In this last unit, we are going to focus on something called a mathematical model. Now, there are many types of mathematical models, and there's too many to get into all of them in this class. So we're going to focus on two very important and simple basic models called a linear model and an exponential model. Now, first we need to talk about what a mathematical model is. And a model is something that we use to represent something real in our life to help us understand it, estimate it, or to make predictions. And the model is designed or formulated based on the relationship between two quantities. So I want you to think about maybe like a map. A map is a model of a particular area, and we use it to estimate distances, to see what roads to take. It's something that we use to help us with our daily life. And so that is one example, a map of a mathematical model. Now, a tool that we use to model everyday things is called a function. A function is a tool used to describe a model. We have inputs and we have outputs, and each input is going to have its own unique output, and that's what defines a function. It's the relationship between two quantities where each of the inputs has one unique output. And the set of all the possible inputs is called the domain. And that I want you to think about as like the x's. When you think about a function, typically our mind goes to equations because that's what we're used to doing in school and in our algebra class. And an equation is one kind or one way that we can represent a function, but that's probably what you're most familiar with. So when you think about inputs, think about your x's. You're plugging x's in. That's why it's called an input. And then you're taking something out, that's your y. You get something out when you put something in, and the set of all the inputs is called the domain, and the set of all the outputs is called the range. And so these are our variables. So one example might be the time of day versus the temperature. So at a certain time of day, it's going to be a certain temperature, and you might check that like maybe on a chart or on your temperature gauge. And so your input would be the time of day, and then what you're looking at, what you get out of it, is the temperature. Now, we have what's called the independent variable and the dependent variable. So the inputs, what we're plugging in, those are our x's, but another way to describe that variable that we're inputting is called the independent variable because it does not depend on anything. It's completely independent of that second variable. The second variable we call the dependent variable. Those are your outputs or your y's because that depends on what you plug in for x. Y is going to change depending on what you plug in for x. So y depends on x. So we want to think of our outputs and our y values as the dependent variable and our inputs and our x as the independent variable. Now, there's all different ways to represent a function. We're going to focus on a few of the most common ways, but just be aware that there are other ways to represent a function than what we're covering here. All right, so we have what's called the numerical representation, which is just a fancy way of saying a table of values or a set of ordered pairs, where each x is paired with each y. So this is an ordered pair, 0, 1, or you can look at it in table format. So this 0 is being mapped to this 1. This 2 is being mapped to this 3. This 4 goes with the 5, and the 6 goes with the 7. So I would describe, if I was looking at the function as just these values in the table, I would say my domain is the set of all my inputs, which is 0, 2, 4, 6. My range is the set of all my outputs, or my y, so that'd be 1, 3, 5, 7. Now, sometimes it can include the values in between. You just got to read the problem or the situation and decide how you want to write it out. Now, if you are including the values that are in between, and these are just a few of the values, you might want to say all the values between and including 0 and 6, rather than just writing it out as 0, 2, 4, and 6, because you want to include all those values in between. And again, that's something that you just have to decide depending on the content of the question. Okay, the next method that we're going to talk about is the symbolic representation of a function. And that is just a fancy way of saying the formula or the equation. So in this, let me scroll back up here a little bit. So using this table, we could easily come up with an equation that represents this table. So this would be the symbolic representation of this function. So if you notice, all the y's are one more than the x's. So you can set up the equation as y is equal to x plus 1. So whatever x is, you just add 1 and you get out y. That's why x is independent and y is dependent, because depending on what you plug in for x, y is going to be whatever x is plus 1. Okay, now the next representation is called the graphical representation, which is pretty self-explanatory. It's the graph of whatever it is that you're talking about. So I plotted the points 0, 1, 2, 3, 4, 5, and 6, 7. So here's the graphical representation of that function that we're talking about with the table. And when we look at the equation y equals x plus 1. Now, if you're talking about all the values in between, you want to make sure that you draw a line to include all those values in between. If you're just talking about those specific points, then you just label them with points. So again, that would be up to you to decide what would be best based on the situation, but just keep that in mind. The verbal representation is exactly as it sounds. You describe the function in words. Now, with the example that I gave you, I didn't put it in the context of certain variables like speed or miles or anything like that. So I'm just generically writing down a verbal description of what we graphed and the equation in our table above. And I just said we're going to add 1 to the input to obtain the output. Now, if this was talking about temperature or speed or something very specific, you want to make sure that you include those terms and those units in your description. And so as the input increases, the output increases, right? Because as x gets bigger and bigger, y, you just add 1 to it. So you have as x increases, y also increases. So this is our verbal description, where we literally say what we're talking about in words. Okay, let's look at our first example to start practicing these concepts. Okay, it says, in the following situation, state whether the two variables are related in a way that might be described by a function. If so, identify the independent and dependent variables. So here's the situation that's given to us. You have an expensive phone bill and want to know how the cost of the bill depends on the amount of time you spent on the phone. So we have two variables here and we're trying to compare them. The variable is the cost of the bill and the amount of time you spent on the phone. This can be described as a function because for each amount of time, so 10 minutes, 20 minutes, 15 minutes, you have a value of y, a specific cost, okay? And the cost depends on the time. So therefore, the cost is the dependent variable because the cost depends on the time, and the time is the independent variable. And then we can also describe it, right, as the time increases that you spend on the phone, of course, your bill is going to go up, so your cost increases. So we can also describe the relationship between those two variables as well. As one increases, the other one increases. Now I could also describe it as time decreases, the cost decreases. That would be another way to state it. Okay, let's look at the next example. Write a short statement that expresses a possible relationship between the variables. You have a rate of pedaling and the speed of a bicycle. So these are two variables. Which one relies on the other? The speed of the bicycle is going to depend on how fast you're pedaling. So the speed of the bicycle is going to be the dependent variable, and the rate of pedaling is going to be your independent variable. So we can say that this is described as a function because the speed of the bicycle depends on the rate of the pedaling, and as the rate of the pedaling increases, the speed increases. And something else that I didn't mention in there, for each speed or each rate that you're pedaling, you're going to have a specific speed of the bicycle. So this is a key to understanding why this is a function. Okay, now, so the examples that we looked up, the two previous examples, those were verbal examples where we discussed and we explained the function verbally. Let's look at a couple of graphical examples as well. So use this graph to answer the following questions. Now, this graph isn't a straight line, and as I've said before, in this unit, we're going to talk about two specific kinds of models. We're going to talk about exponential and linear. Linear is literally a straight line when you're looking at it in terms of a graph, and exponential is going to have a curve to it. If it's decreasing going left to right, that's called exponential decay. If it's increasing going left to right, so if it looks like this, that's going to be called exponential growth. In this case, we're going to be talking about exponential decay. All right, so if we look at this graph very carefully, we see our input, or our x variable, is the altitude in feet, and the y, or the output, or our dependent variable, is the atmospheric pressure in inches of mercury. So we're going to use the graph to answer the questions. And I tried to mark it up here so that as we're talking, you can see where I was looking on the graph. Okay, so this says estimate the pressure at altitudes of 6,000, 18,000, and 29,000 feet to the nearest integer. So if we look at this, the altitude, that's our x, or our independent variable. That's this horizontal axis here. So if I come across and look at 6,000 feet, I labeled it here as 6, and I come up and I try to figure out what the atmospheric pressure is, it's a little bit below 25, so I estimated it at 24 inches of mercury. At 18,000 feet, that's a little bit less than 2,000, so I labeled that right here. I came up this way, and it looks like it's at 15 inches of mercury. At 29,000 feet, that's a little bit less than 3,000, or sorry, 30,000. So I come up here and I come across, and that looks like about 10 inches of mercury. Now, for part B, we're working backwards. Estimate the altitudes at which the pressure is 23, 19, and 13 inches of mercury. So now we're looking at the values on the y-axis, or the dependent variable, and we're going to use that to find our independent variable. All right, so at 23 inches, now this one I did in red so that you can see the difference. So part B is in red. So about 23 inches of mercury is about right here. So if I come across and come down, that would give me about 8,000 feet. The next one here was at 19 and then 13. So let's look at those. At 19, that's a little bit below 20. So when I come down here, That's going to be about 13,000. Here's 10,000. Here's 20,000. So this is 15,000 right here. So a little bit less than 15,000. I'm guessing it would be about 13,000. Now at 13 inches, that would be somewhere around here. I come across, that's this value right here, and I come down. I estimated that to be about 22,000 feet because this is the 20,000 mark. Here's the 25,000 mark. So it's going to be a little bit past 20,000. So I was estimating at about 22,000 feet. Part C says, estimating beyond the boundaries of the graph, at what altitude do you think the atmospheric pressure reaches 5 inches of mercury? And we're going to round to the nearest 1,000. So if we look at 5 inches of mercury, that's right here. But if I come across, it's past this blue model here. The blue model stops here. So if we imagine that this gets extended, that curve, and we talked about that being an exponential decay because of the way that it's shaped, okay? If I come down, I'm going to estimate that it's going to touch 5 inches right about here. Here's my 5 inches. Now, here's 30,000. I'm estimating that 40,000 is about right here, which means this is about 35,000. So I'm estimating that this right here where it crosses would be about 37 to 38,000. Part D says, is there an altitude at which the pressure is exactly zero? When we talk about exponential decay, and we'll talk about this more in depth in the last section of the class, but when we talk about exponential growth or decay, theoretically, that line or that model is never going to touch the x-axis. It's just going to keep getting closer and closer and closer, but it will never touch it. So theoretically, we would say that this would never be zero because it would keep getting super, super close to zero, but would never actually touch that horizontal axis and actually hit zero. Now, this graph here looks more linear to me. So the example we just did looks, because it had a curve to it, looks more like an exponential model. This is more of a straight line. It's not an exact straight line, but it's closer to a straight line. So this to me looks more linear. And now it says, consider the graph of the function below. We want to determine what the independent variable is. Now remember, the independent variable is the set of your inputs, or you can think of it as your x quantity. And so my x quantity, what's on my x-axis or my horizontal axis, is the year. So the year is going to be my independent variable. The dependent variable is my y variable or my output. So in this case, if I look at my y-axis or my vertical axis, that is the world population in billions. So we can get all that information just by taking a look at the graph. The domain of the function, so if we look at this function where the line is drawn, we start at 1950 and we go up to 2000. So it's going to be all the years from 1950 to 2000. And that's because, remember, the domain is the set of all your x values. And in this case, because there's a line in between, we're including everything in between there. So we can say literally from 1950 to 2000. The range is the set of all your y values or all your outputs, right? And if we look at the range, remember the range is the population. So that's going to be from a little bit above 2 to 6. So we're going from here up to here. We're looking at the y values here. So we're going to say a little bit over 2 billion. So I estimated it at 2.3. It could be 2.2. It's hard to say, but I estimated it at 2.3 billion to 6 billion. And again, I can't stress this enough. The domain are the values that represent your X. That's the set of all your X's, and the range is the set of all your Y's. And a way that it helped me remember when I was learning this the first time, X comes before Y in the alphabet, and D comes before R in the alphabet. So domain goes with the X's, and the range goes with the Y's. That's always something that helped me remember which one was which. Okay, so now describing this function in words. This function describes the world population given the year, meaning if I plug in what's known, my given value or my input, I plug in the year and I get out the world population by looking at the graph. So our input or independent variable is our years, which we talked about. Our dependent variable is the world population. So we put something in, we get something out. That's what we put in, the years, and we get out the population in billions. And then we can also describe it by looking at the way the line tilts. As the years increase, the population increases, and that's what makes it go up from left to right. Okay, the last example we're going over is a table example. So this is one of our numerical representations or set of ordered pairs where we have the speed as our X's, the stopping distance as our Y when we're talking about stopping distance of a car. So here's our X, and it's paired with 12. Our 20 is paired with 46. Our 30 is paired with 77, etc. So the independent variable in this case is going to be the speed. The stopping distance relies on the speed of the car. So the speed is going to be independent and the dependent is going to be the stopping distance. The domain are all the values of X. And in this case, our X's or our inputs are the speed. So we're going to say it's the speeds from 10 to 70, and that's in miles per hour. So our range goes from 12 feet to 308 feet. That's all of our Y's here, from 12 to 308. Now, a quick summary of what we talked about. Let's go back up to the top again. We have mathematical models that we use to represent some kind of real-world situation. And we use function as a tool to do that. And functions can be tables, graphs, equations, or written in words. And these are the tools that we use to describe a situation so that we can study the situation and make estimations or predictions. And this is used in all kinds of fields. It's used to predict weather. It's used to predict financial situations, whether you're going to get a profit or a loss. There's all kinds of different models out there. And then in the last two sections of this unit, the next section, we're going to talk about a specific kind of function that we can use to model called a linear model. And then the last section, we're going to use exponential models to model situations. And I also want to stress that these are not the only two kinds of models, that these are just the most common that is used. So there's plenty of other models out there. So just keep in mind that this is just a brief introduction to modeling, and there's all different ways out there to model real life situations.